Welcome everyone, I am JJ. Let's tackle an example problem. So we're saying in this one, let's draw the shear moment diagrams for the beam that we have here. The support reactions are given in our free body diagram. Basically, I'm just assuming at this point, we know how to find support reactions. Let's move the video along. We have enough other stuff to cover. Let's not stress out about finding those. On a homework assignment, you'd almost certainly have to find them. But for our videos, we're gonna go ahead and give them. If you need help finding those, take a look at earlier videos. Let's jump in and shear moment stuff. So we're trying to find what are our shear and moment diagrams. So to figure this out, we need to figure out where does our loading change. We work left to right across that. Anytime we have a distributed load starting, ending, a concentrated force, or a couple moment applied, we need to make a new section. So as I leave A, everything stays the same until I'm at the right edge of my beam. Really, I can do this in one interval here. So this is one interval for our problem. One interval from A to point B that we're coming in and working with on this. I'm making a cut in my section somewhere in between A and B. So I'm going to show that loosely in the middle. I'm going to avoid the 3 kilonewton label, but go from there. And I'm going to make a free body diagram that goes all the way back to the left edge. So I need to include AY in here and that first 4 meters of my distributed load. So let's come in and draw that in. If I'm making a free body diagram, I have just a line for my beam. This is my cut point, P. In here I have AY, we were given, was 12 kilonewtons. My width of this is X. I don't actually know X right now, but it's going to be somewhere between 0 and 12. 0 and 8. Sorry, not 0 and 12. Let's actually make that comment. 0 is less than or equal to X, is less than or equal to the right edge of our beam, 8 meters in. Or we could drop the less than or equal to, drop the equal to part, and just say it's between 0 and 8. From a math standpoint, that is different. From an engineering standpoint, we're saying the same thing. But I need on the top of this a distributed load as well. My distributed load goes straight down. At my cut point, I have my shear. Should be positive going down, so that causes a clockwise rotation about the uncut end of the section. That's just our general sign convention for shear. And my moment should be trying to squish in and compress the top, lift that cut edge up to cause a compression on the top of the beam, tension on the bottom, matching our sign convention here as well. That would be M. And I just want to get equations for V and M in terms of X. I can apply equilibrium to do that. So let's start with my Y, summing forces in the Y direction. I have 12 going up. I have my shear coming down, minus V, and that distributed load that was 3 kilonewtons per meter, also coming down. So minus the area of the distributed load. My base is X, my height is 3, minus 3x equals 0. And I can solve that for my shear. V equals 12 minus 3x. V equals 12 minus 3x. If we think through the shape of that, 12 minus 3x, that's like a y equals mx plus b equation. Negative 3 is the slope. 12 is our intercept, b. This is a linear function. So when I plot this, I should be plotting a nice linear line for everything. But from there, let's check our boundary conditions. I want to know what's happening at 0 and at 8. So we'll put in those. At x equals 0. 12 minus 3 times 0 will get us that our shear is 12. So that's going to be my starting point in here. I am at 12. My next boundary condition will be what happens at x equals 8. At x equals 8. My shear will be 12 minus 3 times 8. I'm going to get negative 12 here. V equals negative 12. So I start at 12. I know at the end of the beam, I'm out here at negative 12. Labeling those 12, negative 12. And it's a linear plot, so it's just a straight line to connect the 2 points. Is my entire shear diagram. And I can shade that in just to make it look nice. It's easier to read if it's been shaded in. That's my shear diagram. For the moment, I can sum moments up about my cut point. So with positive going counterclockwise, summing my moment about point P is going to get me, well, I have that internal moment, M. My distributed load would cause a positive rotation, so plus area 3x force times distance from P to the middle of the rectangle would be half of x times x over 2 minus my moment from my AY minus 12x is going to get us to 0. Or solving for my moment, I'm going to get the equation M equals, moving everything to the other side, 12x minus 3x squared over 2, or minus 1.5 x squared, same thing. But from here, we just check our boundary conditions again. At x equals 0, putting 0 in for this. 12 times 0 minus 3 times 0 squared over 2. Our moment is 0. Our second boundary condition, let's actually put a dot here. So we're starting out at 0, somewhere over here. Our next boundary condition, what happens at x equals 8? So 12 times 8 minus 3 times 8 squared divided by 2 is actually going to get us our moment is 0 again. At the end of our beam, we've come back down, and we're still at 0. What happens in between here, though? Can we figure that out? Well, let's just logically think that through. If this is a constant, if our m equals 0, we would have a straight line. It's not, though. I have a x squared term in here. This should be quadratic. And I need to figure out where does this increase or decrease down to. I have a negative x squared, so it should be concave down. Should look generally like this from the negative x squared. So I know it should increase up and then come back down. I have a max point in here. How do I find where a function is maximum at? I just need to figure out what dm dx would be. So my derivative of m, dm, derivative of moment with respect to x, is going to get me, well, 12x will just become 12, negative 3x squared over 2. That squared would cancel the 2 on the bottom, and we'd be left with minus 3x. Have we seen this equation before? We definitely have. The derivative of moment with respect to x is 12 minus 3x. That is my shear. That will always be true for us. Moment, or shear, is the derivative of moment with respect to x. Which means to find that max or min point, I really want to say, where's my shear equal to 0? So let's come back up and do that. When v equals 0, so 0 equals 12 minus 3x, we're now solving for x. So we can move the 3x to the other side, 3x equals 12. Solving that, we get that our x equals 4. When shear is 0, x equals 4. And that's going to become one last critical point for us. Because if this is 0 right here, at this point, and it is 4 meters from the edge. We just found that. 4 meters. 4 meters. That means that's our 0 shear. That should directly correspond to a maximum moment in here. That our moment should parabolically increase up and come right back down. We're not going to worry that my scale's a little bit off here. That should be right in the middle of everything. 4 feet from either, or 4 meters from either edge. But we know we're going to increase up to that max point. I just need to find that. That's going to be one last critical point in here. So at x equals 4. We know that should give me my max point because the derivative of moment is 0 there. Where the derivative is 0, our function is at a max or a min. So at x equals 4, putting that in, 12 times 4 minus 3 times 4 squared over 2. My moment comes out to be 24. So I'm going to increase up to 24 kilonewton meters and then come back down to 0 to finish out our moment diagram. Again, just break this into intervals, come up with equations, check our boundary conditions. Really, anytime that our shear slopes across the x-axis, like we saw right here, we need to figure out where that's at so we can get that into our moment calculations. If it abruptly jumped over the x-axis, it doesn't matter then. But we did see a nice gradual slope across. We have to find it. But hopefully this is a useful video for you. If it was, hit those like and subscribe buttons. Stick around. Watch more videos. Let's get you an A with JJ.